Okay, everybody, tonight we have a triangle problem where two of the sides are constant. Two of the sides are constant and one side is variable. It's a log base 2 problem. Now, clearly, log base 2 of 7 is the smaller number in this list, or at least it's smaller than this leg right here. So we could think of log base 2 of 11, or excuse me, we'll call this log base 2 of 7, I'm sorry, because it's a smaller number, right? It's a number somewhere between 2 and 3, in fact, since 7 is between 2 squared and 2 cubed. Okay, so it would be the smaller number in the list. And the way things are labeled, this would be log base 2 of 11. And we're going to assume that log base 2 of n is the larger of the ones. But we have to actually consider two cases. Okay, so we're going to take advantage of this triangle inequality circumstance where the longer side is always less than the sum of the lengths of the other two sides. Okay, that's called the triangle inequality. All right, now we still have to break it into two cases because it's possible that log base 2 of n would be larger than log base 2 of 11, or it's possible that it would be less than log base 2 of 11. We're focusing on log base 2 of 11 since it's a larger number than log base 2 of, the other side, the shorter side, okay, log base 2 of 7, excuse me. All right, so, but in any event, we're going to go ahead and start out by assuming that log base 2 of n is a larger number than log base 2 of 11. Okay, and then if you remember, there's a very well-known property of logarithms that says that the log of the product, any base, the log of the product is equal to the sum of the logs. Okay, and that just follows from laws of exponents. Very straightforward proof in a college algebra class. So, again, dropping the base here because it's true for all bases. Log base A plus, log of A and then log of B. So sums get converted into products. Okay, here we go. And that's exactly what happened right here, folks. We have log of A times B, which would be 7 times 11 in this case. Okay, that's what happened from here. 7 times 11 from this sum got converted to a product for a single log. Okay, now what does this information do for us? Well, it's kind of nice because we can think in terms of powers of 2. The largest power of 2 that would be less than this would be 2 to the 6th. Let me write it over here. 2 to the 6th is equal to 64. Right? So 64 is certainly less than 77. Now notice that 2 to the 7th would be larger than 77. 2 to the 7th is 128. All right, now I'll omit the powers here, but the next power that would be in this list would be 32. 2 to the 5th. 2 to the 4th is 16. And again, we're looking for values of n that satisfy this logarithmic inequality. 2 cubed is 8. 2 squared is 4. And finally, 2 to the first power is 2, right? So all these numbers would satisfy this circumstance under the assumption that log base 2 of n was larger than the longer fixed leg, okay? Okay, but now case 2 would be, what if log base 2 is less than or equal, log base 2 of n is less than or equal to the longest fixed leg, all right? Now that's just a very similar step, except we'll be using a difference. You'll notice here, I won't write the steps, but if you subtract log base 2 of 7 from this side, you get log base 2 of n is equal to log base 2 of 11 minus log base 2 of 7. And there's a quotient property that we used. All right? Okay, so notice here now, and that property is that the log of a quotient is the difference of the logs. Okay, and that you'd have the difference of the logs if you subtracted log base 2 of 7 from both sides of this inequality. All right, but what's the first value of n that's going to fit for this list? That would not, 2 wouldn't work, right? 2 is greater than 11 over 7, right? So you would have to put 4 in here, right? You would have just 2 to the first. So you would have to include what in this list? Okay, the very same thing here. 2 is larger than 11 over 7, so you would have 2 4, 8, 16, 32, 64. But since it's greater, we could just keep going forever, right? Ad infinitum. 128 is 2 to the 7th. And I'll put the customary ellipsis right here. So again, these lists look quite similar, but this one has 64 as its largest element. 64 is the largest power of 2 that satisfies this inequality, whereas right here, we share a lot of common elements here, but numbers larger than, powers of 2 larger than 64 satisfies this inequality. So what do? We take the intersection. We definitely take the intersection of these two sets, and that intersection, of course, would be 2, 4, 8, 16, 32, and we stop at 64. Again, so that the two sets intersect at precisely these 6 values. And so we can write this as the solution set. This is the set of ends that actually satisfy both of these inequalities. Okay? So I kind of like that problem. There's 6 values that actually would form triangles. Notice these are the only ones, but the log function is a one-to-one function. We don't have to worry about it oscillating and repeating values. So these would be the only 6 values, the only powers of 2 that would satisfy. And we don't have to worry about any other weird things happening. These aren't sinusoidal or periodic functions. The log function is a slowly increasing function, and it is a one-to-one function. So these are the only values, the 6 values, that would satisfy the conditions, meaning there would be 6 triangles. Okay, in other words, if you want to think of it in those sense, it said find all the ends, but there would actually be 6 triangles that met these constraints. So there'd be 6 triangles. All right, y'all, that is it. Let me know if you saw any flaws in the reasoning there. But again, I think breaking it into 2 cases is the soundest way to handle a problem like this. And then we literally use this inequality twice. The roles swapped for the longer side, but it's still the same kind of reasoning. Okay, case 1 and case 2 utilize this result. Okay, all right. Thank you for viewing.